Okay, so talking about similarity, similar shapes. So first off, we have things that make objects congruent and or similar, and those are rigid transformations. So a translation, just sliding along the xy plane, a reflection, so taking a line and folding it along that line and reflecting it across or doing a mirror, and a rotation. Now the key things with those rigid transformations is what do they preserve? Well, they preserve side length and angles. So they preserve distance and angles. That makes them rigid transformations. That means all of these objects that we've translated, reflected, or rotated are congruent to the original figure. They're also similar with a scale factor of 1. Now, who preserves angles but not distance? Well, that's going to be similar objects, and those are non-rigid transformations. And what are those? That's a dilation. So as we take a look, that dilation changes the side, changes the distance. Okay. So the first example, we're going to identify the transformation or transformations that occurred to transform rectangle ABCD to rectangle A prime, B prime, C prime, D prime. So we look, it just looks like that translation example that we've got from the beginning. And let's see, all you have to do is count from A. So let's see, it looks like it went right and up. So right 1, 2, 3, 4, 5, 6, 7, 8, 9. Right 9 and up 1, 2, 3, and up 4 units. Okay. Example 2, we've got triangle ABC is isosceles with AC congruent to AB, so those are those line segments. In your own words, describe how transformations and the properties of rigid motions can be used to show that angle C is congruent to angle B. So start with, we construct a perpendicular bisector of that base of CB. So if we cut that in half and then reflect angle ABC across that perpendicular bisector of CB, that would show that if angle ABC lines up with angle ACB, then they match, and that would show that they are congruent. Example 3, we're given that angle A or side AC is congruent to BD and CB is congruent to CD. We want to prove that triangle ABC is congruent to triangle ADC. Okay. So we're going to do a 2-column proof. On the left are the statements, on the right is the reason. First off, CB is congruent to CD. That was given. We also know that angle or side AC is perpendicular to BD. That was given. With that, we know angle BCA is congruent to DCA. That's the definition of perpendicular lines, because AC is perpendicular bisector, or is perpendicular to BD. That tells us that the two angles on either side have to be 90 degrees. So that means that the angles are equal, and then side AC is congruent to AC. Well, that's kind of obvious, but we do have a name for that. That's by the reflexive property. That's just telling that it's the same line. You can also have by the reflexive property for the same angle. Therefore, triangle ABC is congruent to ABD by side angle side. How do we know? Well, AC, we just said, was congruent. Well, let's start with the first side. CB and CD are congruent, so those sides. And then the angles are equal, and then AC is congruent to itself. That shows that it is congruent. And you can also look at the similarity notes that we had for the power focus area for some of those definitions. Now, we've got some practice. I've got 4 problems here that are asking you to do some very similar things, and then check them with me. Example 4, we want to derive the distance of the line segment below in terms of A, B, C, and D. We want to sketch the image below to justify your derivation. So you've got it sketched already. You just need to add some stuff to it. So start with adding in some lines. I got the distance from A to C. That's the horizontal distance. And I got the distance from B to D. That's the vertical distance. Oh, it looks like a right triangle. Wait a minute. we have something from an earlier math class that helps us with that. Pythagorean theorem. Because if I know the lengths of the legs, I can square them, add them, and I'll get the length of the hypotenuse squared. So this makes a right triangle, so we use the Pythagorean theorem. A squared plus b squared equals c squared. Our horizontal distance, that's the distance from A to C, so I could just do C minus A, that's squared. The vertical distance is from B to D, so I could do D minus B, that quantity squared. That should equal the hypotenuse. In this case, we're going to use D for the hypotenuse. And then I would want to square root both sides to get just the distance. So the distance between 2 points is the formula. Square root of C minus A quantity squared plus D minus B quantity squared. That sum square rooted. Okay, so here we have example 5. We have rectangle ABCD is dilated with a scale of factor 2 centered at 1, 1. Well, what are the coordinates of the new figure? Well, what helps is to draw some lines. And sometimes you can just not draw the lines, but kind of count it as you go. So putting down the point that we are dilating from, so 1, 1's plotted, and let's just take a look at C. To get from that point 1, 1 to get to C, I have to go up 1 and left 1. Since it's a scale factor of 2, that means I follow those directions twice, so I just extend that line out. So the new point for C is going to be at -1, 3. So that's C prime. Now let's do D, so count 1, 2, 3 down and 1 left, so then count again, down 2, 3 and 1 left. We end up at -1, -5 for D. And then for A, we go down 3 and left 5, so down 3 and left 5 again, we end up at -9, -5. And then for B, we go up 1 and left 5, so up 1 and left 5 again is at -9, 3. Okay. And so we can draw the new rectangle, or in this case square. What generalization can we make for the side lengths? Well, the original side lengths are 4 units long, and the new side lengths are 8 units long, so we just all of the side lengths doubled from lengths of 4 to lengths of 8, so we just always take the scale factor times the original length to get the new sides. What generalization can we make about the area? Well, the original area is 4 by 4, that's 16. Well, it kind of looks like I could fit 4 of those in, so we take the area was quadrupled, so we take 2 squared, or 4 times the original area to get the new area. In practice 5, we want to know if the figure is a rectangle or a square, or both, or neither, and justify your response. Couple hints. Use the distance formula to figure out the lengths of all the sides. If they're all equal, then it could be a square or a rhombus. To be a square, all of the angles also have to be 90 degrees. So you would have to figure out the slope of each line and see if they are perpendicular to each other. Okay. If you need a refresher on what perpendicular and parallel lines, what their slopes look like, ask. And then practice 6 is just like example 5 that we did. I've just changed some of the numbers. Practice 7 is continuing with some of that work with dilation. Practice 8 is also working with similar figures and seeing what we can figure out about those. So if you're having questions, make sure you're asking. And then the last part is working with finding trig ratios, and you should have taken the notes for that power focus area already, but some of the key highlights: sine with a right triangle is so, opposite over hypotenuse. So sine is opposite over hypotenuse. Cosine is ca, so cosine is adjacent over hypotenuse, and tangent is toa. Tangent is opposite over adjacent. And then that's, if I have the angle, how I can find the ratio of the sides. If I have the sides and I need the angle, we do sine inverse of the ratio will get us the angle, or cosine inverse of the ratio will get us the angle, or tangent inverse of the ratio will get us the angle. So looking at example 6, given the triangle below, and A is 5, B is 12, and C is 13, what are the values of the sine of A, cosine of A, tangent of A, sine of B, cosine of B, tangent of B? Well, always just find the angle that we're looking from. So angle A, and opposite of that is 5. The hypotenuse is 13. Cosine of A, that's adjacent, and the adjacent is 12. The hypotenuse again is 13. Tangent is opposite, which is 5, over adjacent, which is 12. And then sine, we switch what angle we're looking from. So for B, opposite is 12. The hypotenuse is still 13. Adjacent, though, is 5. And the hypotenuse is 13. Tangent is 12 over 5. Okay. So you might be thinking about why we have the same values, same fractions, just in different spots depending on what angle I am looking at. Example 7, we've got boats moving from the top of a 150-foot cliff moving away from the cliff. The angle of depression of the boat changes from 45 degrees to 14 degrees in 2 minutes. Find the speed of the boat to the nearest foot per second. So we've basically got someone standing on top. We've got this representation here. The first one would be the small triangle, because that's the 45 degrees angle of depression. So notice that makes a 90-degree angle, so that's still 150 feet. We'd like to know how far out it is, x. We know the angle that we're going to have is 90 minus 45, which is 45. And then we've got the long triangle, still 150 feet tall. We got y. And then we've got 90 minus 14, which is 76, will be that other angle. So both of those are working with, if I'm working with the 45 or the 76 to find that side opposite, that's opposite over adjacent, that's tangent. So tangent of 45 equals x over 150, and tangent of 76 equals y over 150. Well, the tangent of 45, well, to get x by itself, we'd multiply by 150 on both sides. That just, and same on tangent of 76 times 150. So x happens to be 150 feet, and y is about 602. I'm rounding to the nearest foot. Okay. So how far has it traveled? Well, the total distance away from the cliff is 602. The first distance was 150, so just subtract them. So the total distance is 452 feet. But that's not quite what it was asking. It was asking how fast the boat was going. So distance is rate times time. I've got the distance and I've got the time. Distance, so divide by distance by time will give us the rate. So 452 divided by 2 gives us 226 feet per minute. Turn that into seconds. Well, there's 226 feet per minute. That's times 1 minute over 60 seconds, so the minutes cancel and we'll get feet per second. And that's about 4 feet per second is how fast the boat is moving. And now practice 11 and 12 as you try the same stuff. And then check them with me.